Our first presenter is Lauren Zundel from the University of New Mexico. Her field is physics, and she did her practicum at Brookhaven National Laboratory. Lauren.
Thank you. Thank you. As mentioned, I'm Lauren Zundel. I'm at the University of New Mexico, where I work in the theoretical nanophotonics group with Professor Alejandro Manjavacas. So I've said that I work in theoretical nanophotonics. What is that? Well, nanophotonics is the field that is interested in understanding the interactions between light and nanoscale matter. And in particular, I have focused my CSGF years in my dissertation research on trying to describe the optical response of periodic arrays of metallic nanoparticles. And in particular, I've investigated a few different problems over the years, such as how we can manipulate the optical response of these systems, periodic arrays of nanoparticles, by changing the parameters of the system, and also how to manipulate the response by changing the nature of the light that you use to excite the system, what you shine on the array. And in addition, we've looked at just some different opportunities for actual applications that would maybe make these things useful. But all of this hinges on the idea of metallic nanostructures supporting surface plasmons. Surface plasmons are a type of resonance that are the collective excitation of the conduction electrons of a metallic nanostructure. What does that mean, though? That's pretty technical. Well, if we have a metallic structure of some sort, we can understand its charge distribution as positive charges that are stationary. They can't move around. They form an ionic lattice. And electrons that are free to move around the system. These are known as conduction electrons, and they're characteristic of metallic materials. So if we take, say, a metal nanosphere, and we shine light on it, we're going to drive away the electrons from their equilibrium position. So we're shining light that has some frequency, and we're driving these conduction electrons away from their equilibrium positions at the frequency of this light. On the other hand, we also know from freshman level physics that there is an attractive Coulomb force between positive and negative charges. So on the one hand, we're driving the electrons away from their equilibrium positions. And on the other hand, we're pulling them back in with some natural frequency of the system that depends on things like the geometry and material of the nanostructure. This might sound kind of analogous, if you think just for a second, to a system like a damp-driven mass on a spring. And just like a damp-driven mass on a spring, this system supports a resonance. And this resonance has a special name, which is a localized surface plasmon. We're interested in localized surface plasmons because they have some really extraordinary abilities. And in particular, one that I want to just highlight is that they can produce extremely strong field confinements and enhancements. So if we take a gold nanosphere, for example, and shine light on it, exciting its surface plasmon, then the field intensity enhancement in the vicinity of the nanostructure will look something like this, where in a very sub-wavelength region around the surface of the nanosphere, we can get field intensities that are about 10 times as strong as what we initially shine on the system. That's pretty good, but actually we can do better if we use more complicated geometries like 2 gold nanospheres, separated by a very sub-wavelength gap of only 10 nanometers. So just for reference, the plasmon resonance happens at about 500 nanometers, so this gap is very, very sub-wavelength. And if we excite the plasmon in this system, then the field intensity will look, will look like this, where it's completely confined to this small gap between the 2 nanospheres, and because it gets so confined, it can reach intensities of about 100 times what we initially shine on the system. So what this tells us is that while single metal nanostructures are good, to really leverage the potential of surface plasmons for different applications, we need to be more creative. We need to use more complex geometries. And one geometry that we're very interested in is a periodic array. That's because periodic arrays of nanoparticles support collective modes known as lattice resonances. Lattice resonances occur at wavelengths that are commensurate with the periodicity of the array, so the spacing of the nanoparticles. And in addition, they give rise to extremely strong and spectrally narrow optical responses that make them useful for a wide range of applications. For instance, periodic arrays of metallic nanoparticles have been studied for things like nanoscale light sources and nanolasers, so to produce coherent light. For ultrasensitive biosensing, so already single metallic nanoparticles or solutions of metallic nanoparticles are used for things like COVID tests and before that pregnancy tests, but periodic arrays are also a really promising platform for these sorts of things. and also for very vivid, high-resolution color printing. In addition, periodic arrays of nanoparticles have been exploited to explore novel physics phenomena, things like Bose-Einstein condensates. So, I mean, the sky really is the limit with these things. There is so much potential, but in order to fully leverage this potential, we need a complete theoretical understanding of the optical response of periodic arrays of nanostructures. And that's where my group comes in. In the past, the excitation of periodic arrays of nanostructures and the lattice resonances that they support has been studied extensively for the case of plane wave excitation. So if you don't know what that is, a plane wave is just essentially a wave, an electromagnetic wave that is perfectly spatially delocalized. So it really is just a very idealized theoretical object. You can't have a plane wave in real life. You can get very close to it by just having a beam that's wider than the thing that you're exciting, but it really is theoretical. And these have been studied extensively in the past. The vast majority of studies of lattice resonances have considered plane wave excitation. On the other end of the spectrum, we have excitation by something that is perfectly localized in space, like a point dipole. And actually, if you came to my poster at last year's program review, you heard all about the excitation of lattice resonances by point dipoles, because that was what I presented on last year. But this year, I want to present on what happens in the middle, when you don't have something that's perfectly spatially delocalized, but you also don't have something that is just one point in space exciting your array. In that case, you would have something like a focused light beam, a light beam of finite width. And that is the exact system that I'm going to be discussing today. In particular, we're looking at a periodic array of silver nanoparticles, in this case, just in vacuum, excited by a light beam of finite width with a Gaussian spatial profile. And so if we look at the optical response of this array, well, for an array period or spacing of 300 nanometers, under plane wave excitation, this is the behavior that we get. Now, on the y-axis, I'm plotting the extinction efficiency. Don't worry too much about what that means. Just understand it as the optical response, or like the amount of light that doesn't go right through the array. It's sort of the light that's removed by the array. And you can see that we have a very strong optical response, a high extinction efficiency, just above 300 nanometers. And this is our lattice resonance. Again, the lattice resonance appears at wavelengths that are somewhat commensurate with the period of the array. So for a spacing of 300 nanometers, we get our lattice resonance above 300 nanometers. Now, what if we were to excite the array instead with a light beam of finite width? Well, of course, you need some parameter that controls the width. In this case, we're calling it W-ints. And you can see that the optical response is somewhat different, and in fact, lower because you're not exciting all of the particles. And of course, if you increase the width of the light beam, at some point you're exciting enough particles, and so the optical response is all in between. It's not very easy to see on this plot, but if we increase the array period, you can see that evolution toward the plane wave limit much better. In addition, just notice that now the lattice resonance occurs above 400 nanometers because the array period is 400 nanometers. And in this case, we need a much wider beam, a much larger value of W-ints, in other words, in order to saturate to the plane wave excitation limit. And this trend continues if you increase the array period even more. By the time you're at an array period of 600 nanometers, for instance, you need a light beam that's about 800 array periods wide, so exciting in all directions, about 800 nanoparticles, in order to fully excite the lattice resonance and saturate to that plane wave excitation limit, that like theoretical ideal. And so just to kind of characterize this transition toward the plane wave excitation limit, I want to note that by increasing W-ints, you're actually influencing two main aspects of the optical response. In particular, you change the maximum extinction efficiency, or the maximum value of the optical response. And that increases with W-ints, as I just said. In addition, as you approach the plane wave excitation limit, please. OK, there we go. As you increase the plane wave excitation limit, you change the width of the resonance as well. And in fact, the resonance kind of narrows as it approaches the plane wave excitation limit. So first, I just want to show you what happens with the extinction efficiency as a function of the width of the light beam for the different cases. In this case, we're normalizing to 1, so 1 would be the plane wave excitation limit, exactly ideal. And again, for the small array period, the convergence is very fast, but it slows as you go to larger and larger array periods. In contrast, if we look at a function that depends on the width of the resonance, in this case the quality factor, which is inversely proportional to the width of the resonance, so it's the ratio between the resonance wavelength and the full width at half maximum of your resonance, we see really the same behavior, that it takes a wider light beam in order to fully converge to the plane wave limit when you have a larger array period. And in addition, I just want to note that lattice resonances supported by arrays with larger periods have larger quality factors. So that really fully kind of explains this convergence to the plane wave limit, and which is much more easy to compute than the response to these light beams of finite width, but of course doesn't correspond necessarily to an experiment. With that, I just want to talk about one application, one possible use of what we've just looked at, which is the idea of thermoplasmonics. So if you have a metallic nanostructure that supports a surface plasmon, one thing that is really exciting about surface plasmons is that they have extremely large absorption cross-sections. So here I'm just showing the flux of energy at the plasmon resonance of a silver nanoparticle. And you can see that light that you would anticipate maybe would pass right by the nanoparticle actually gets sucked right in. So in other words, this particle is absorbing more than its physical area. It essentially has a shadow that is larger than it is, and that's because it's supporting a plasmon. This absorption makes these nanoparticles really good at turning light into heat. And this is exactly the goal of the field of thermoplasmonics, trying to take this light to heat conversion and do useful things with it. And in fact, there are a lot of useful things you can do with it. For example, cancer therapy. If you, in some way, embed these nanoparticles in the area of a tumor and heat them up, that will kill the tumor and do minimal damage to surrounding tissue. And actually, this is really exciting because it is in clinical trials for prostate cancer right now. So that is really exciting and promising. In addition, you can do things that are completely different, like water desalination. That would be super useful, especially out west. We're always in a state of drought. We never have enough water. Water desalination would be very great. Drug and gene delivery, another promising application. Thermophotovoltaics, which seeks to convert wasted heat from things like refrigerators into useful energy. And also more kind of material science-oriented things like nanoscale welding and epoxy photocuring. So really the possibilities of thermoplasmonics are endless, and we wanted to know if we can exploit lattice resonances in order to advance thermoplasmonics applications. So we're looking at a very similar system to what I was discussing before, specifically an array now of gold nanoparticles embedded in water. And if we excite this array with a light beam of finite width for different array periods, this is the behavior that we see. And now I'm just plotting the absorbance, so just the light that the particles actually physically absorb. And you can see a couple of things here. First, as we change the array period from 250 nanometers to 500 nanometers, the wavelength of the lattice resonance increases. That, again, is just this behavior of the lattice resonance, that it occurs at wavelengths that are commensurate with the array periodicity. It's just shifted now because it's in water, which has a different refractive index, so the wavelength in the medium in the water is different. In addition, we actually see an interesting behavior that the absorbance is relatively constant at the peak across all of the different array periods. Of course, this is only true if you use a light beam of finite width that is wide enough to excite the lattice resonance efficiently. And in fact, looking at just the worst case scenarios, so the two arrays with the largest periods, again, those would have the worst convergence to the plane wave limit, we can see that 45 microns in width is wide enough to efficiently excite the lattice resonance in even the worst case. So as I mentioned, at the peak, once you've fully excited the lattice resonance, you get an absorbance of about 0.5, which incidentally is the maximum value that you can get for a two-dimensional system of electric dipoles. Doesn't matter so much, but it's a good absorbance is the point. In addition, we know that the density of the nanoparticles per unit of area scales as the inverse of the square of the array period. So if you increase the array period, you're going to have fewer nanoparticles per unit of area. Makes sense. This translates, though, to an absorbance per nanoparticle that we anticipate should scale as the square of the array period. And indeed, if we look at the absorbance of the center nanoparticle, so in this case, the one that the light beam is centered on, we can see exactly that behavior, that we get this quadratic scaling of the power absorbed by the center particle. Of course, that's only true if you can efficiently excite the lattice resonance. So if you go to narrower and narrower light beams, you do get a dropping off as you are unable to excite the lattice resonance. But as long as you use a light beam that's sufficiently wide, you can get this A² scaling. Incidentally, under pulse illumination conditions, the temperature increase of the nanoparticle is actually linearly related to the power absorbed by the nanoparticle. It's related also to the pulse duration and some properties of the nanoparticle, but the point is that because it's linearly related to the power absorbed, actually this may as well just be a plot of the temperature increase of the particle, or the array, under pulsed illumination conditions. So in other words, we get a temperature increase that scales with the square of the array period under pulsed illumination conditions. Things are a little bit different if instead we have continuous wave illumination conditions, because in that case, the particles are able to thermalize with one another. So in other words, they're exchanging heat with their neighbors also. So now we have a more complicated formula where we have not only the direct absorbance of the nanoparticle itself, but also its interactions with its neighbors. And in that case, we see a very different behavior, that the temperature increase is actually independent of the period of the array. With that, I know that I'm running out of time, but I just want to say a little bit about my use of HPC in this work. The overwhelming majority of my work is embarrassingly parallel. Of course, as you all well know, that doesn't mean it doesn't benefit from HPC. There are a whole lot of things that you have to do when you're computing the response of an array of nanoparticles, things like the inversion of large matrices, doing really complicated integrals that maybe require adaptive integration techniques, computing special functions like a lot of times, like tens of thousands of times. And you have to do that for every single wavelength. So every point on all of those curves is, you have to do all of this. So it demands a lot of resources. Thankfully, at the University of New Mexico, we have access to the Center for Advanced Research Computing, which is an excellent facility that I have made extensive use of over the years, and in return, they have highlighted some of my work. So it's really great. I am very, very grateful for them and for the many thousands of hours that I have put on their systems. With that, I'll just conclude by saying that, of course, in a 15-minute talk, you can only say so much. This only represents a very small amount of the work that I've done over the last 4 years, so of course you can check out maybe some of my other things. And of course, I am immensely grateful to my advisor and my group members, past and present, and also the dog. Thank you.